We started with a differential equation that looked something like this. Right? And we Laplace transformed that. Now notice, this is already in our linear form. Now I'm just, this week is pretty much the last time that I'm going to be writing these t's, right? I'm going to rely on you to intuitively know that if it's a derivative or a differential equation, then the variables are obviously going to be variables of t. And if I've Laplaced that and you see lots of s's around, then the variables are functions of s. But because that's already in that linear form, I'm going to be able to transform that using the Laplace transform to something that looks like this. And I will then be able to write it in this very special version of the linear shape. And I want you to recognize that this is a linear shape even though it looks nonlinear. And I'll show you exactly how. I'll write this. This is what I call the transfer function. And I want to put a very clear warning sign here that in the textbook, and you'll find a lot of sources that define the transfer function as the following result. So if I say this is g of s, right? If I say this is g of s, you'll see the textbook use this form all the time, right? So the textbook almost defines a transfer function as the ratio of the output to the input. Now, I do not like this form because it makes it really hard to reason about functions where there are additional inputs. I would say that h has there are two transfer functions there. One that relates f into h and one that relates into to h. The ratio definition then asks you to do some really complicated mental arithmetic. It says something like, oh, how you get that one transfer function is like you imagine that in2 is 0, and then you still calculate the ratio. And then if you want to calculate the other one, you imagine the other one is 0, and then you still calculate the ratio. In my mind, that's very convoluted and doesn't make enough sense to really give me the yield on this ratio description. So I define the transfer function as the coefficient of an input when I write the equation in the standard form as output is equal to some linear combination of the inputs. You'll see it doesn't change anything in terms of like what you eventually find, but it does mean that you end up with this wonderful symmetry that these relationships are again linear combinations of their associated variables. Now, so these coefficients, you'll see these coefficients, the key thing about the coefficient is that it doesn't include any variables. Okay, so the target is to remove the variables from all the other symbols. So K1 and K2 are constants, and S is not a variable when we do this analysis. Remember, we left out T as a special symbol when we were doing analysis in the time domain. And S is like the brother of T in the Laplace domain. We similarly leave it out. We don't count it as a symbol. It's not a variable. It's not anything, right? It's just not in the analysis. In the same way that we left out T, you will recall we never spoke about T. We never counted T as a variable when we did degree of freedom analysis. We never gave it a name. It's not an input. It's not an output. It's not a parameter. It's a whole different thing. It's completely by itself. S is the same way. And so all you have to do is to manipulate your equations into the standard form where the output is on the left and the other stuff is on the right, keeping in mind exactly the same formalism that we'll read the sequence of causality going right to left. And once we've isolated the coefficients of the inputs, those are the transfer functions. Now, by convention, we'll write those transfer functions, and this is the last little bit of the work that I want you to know for semester test 1. We'll write those transfer functions in a box like this. And we will call this a block diagram representation of that same equation. Now, in the case where we have multiple inputs, I could have another in and another transfer function. Let's call this G1. And I could express this relationship in this way. Now, please note, H is equal to the sum of those transformed inputs, if the equation is the way that it's at the top of the screen right now. Okay? What I have shown you here is every single symbol that is allowed on what I will try really hard to call a formal block diagram. Now, sometimes I'll just slip, and the textbook doesn't make this distinction, but I want to make a distinction between what I call formal block diagrams, which are a one-to-one map to the math, and just block diagrams which may include some other, just like arrows and stuff, to help you explain how data is flowing in the system. Okay? When I see a block like this one, this maps 100% one-to-one to this mathematical structure. This maps 100% to this mathematical structure, and the plus junction maps 100% to this mathematical structure. You can go backwards and forwards. If I give you the equation, you can draw the block diagram. If I give you the block diagram, you can draw the equation. It is 100% wrong. It is never right for a formal block diagram to have any more than one incoming arrow and one outgoing arrow. So for instance, this is wrong. Okay? It is fine for diagrams to include junctions like these that just indicate that those things are all the same. We may use that from time to time. And it is fine for us to have multiple signals coming into a summing junction. We usually indicate the nature of the sum by a plus or a minus, either inside the circle or attached to the arrow like this. Summing junctions can only ever, however, have one outgoing result. And you should consider this to be similar to like how you write the mathematical formula. Like if I say B is equal to, or C is equal to A plus B, there's only one outcome of that. This is the entire constellation of formal block diagrams.